Alright, so in 2.6 we talk about limits at infinity. So in the past we let x approach a number, and the result was that the values of y became arbitrarily large, positive or negative. In this section we let x become arbitrarily large, and we see what happens to y. So we talk about limits at infinity and the horizontal asymptote. So they talk about this function first. They graph it. So you can see if you go up to negative infinity, you're approaching the y value of 1. And if you go up to positive infinity, you're approaching the y value of 1. And if you plug in very larger and larger numbers for x, you get y coordinates that are closer and closer to 1. Makes perfect sense. Alright, now if you take the limit as x goes to infinity, you get 1. We already saw that. For positive numbers it goes to 1. Okay, and so we can write this intuitively as the limit at infinity. This says the limit as x approaches infinity of f of x equals some number L. In that case it was a 1. But you can also note you can approach infinity one of two ways. You can cross the horizontal asymptote and come at it from below. You can come at it from above, or you can wander back and forth across it, approaching that number as well from above and below. Now if you take the limit as it goes off to minus infinity and it approaches 1, that's another type of limit as x goes to negative infinity. And so you would see something like this, where as you go off to negative infinity you're approaching some y value, in this case L. And you can cross your horizontal asymptotes on occasion, and you can approach it in this case from below. Now here's where they talk about how do you show something has a horizontal asymptote. Well, you take the limit as it goes off to infinity or minus infinity, and if it equals some number, then you have a horizontal asymptote at that spot, and it's called y equals L, whatever that number is. So let's say that number's 5. Your asymptote is the equation y equals L, or y equals 5. They talk about an interesting function, the inverse tangent function, which actually if you go off to infinity it approaches pi over 2, and if you go off to negative infinity it approaches negative pi over 2. So it actually has two horizontal asymptotes. It's quite rare, but that happens in this case. Alright, so now they talk about infinite limits, limits at infinity, and asymptotes. First off, just to explain how do you find an asymptote. Horizontal, you have to take the limit to infinity or minus infinity, and you have to be able to show that it equals one number. To find a vertical asymptote, there's several ways. One, if it's a fraction, you can set the denominator equal to 0. And wherever it equals 0 is an asymptote. X equals some number is your equation of a vertical asymptote. There's another way you can show something as a vertical asymptote. That's by taking the left or right-handed limit and showing that it goes off to infinity or minus infinity. That's another way of showing something has a vertical asymptote. So we got a vertical asymptote here at -1 and at +2. We have a horizontal asymptote here at 2 and over here at 4. Alright, so first thing they talk about is if x approaches -1, it goes off to infinity. So you have a vertical asymptote there at x equals -1. Now look at what happens when on the left hand for +2. If you come at it from the left, you go to minus infinity. Come at it from the right, you go to positive infinity. So x equals 2, the number you're approaching, is a vertical asymptote. Now here's where they talk about horizontal asymptotes. If you go to infinity, positive infinity, you approach 4. If you go to negative infinity, you approach 2. So y equals 4 and y equals 2 are both horizontal asymptotes in this problem. So now they say find the limit as x goes off to infinity or minus infinity of 1 over x. Well, here's 1 over x. So if you look at the graph, you'd expect as you go off to infinity, it would approach 0 from above. And if you go off to negative infinity, you would expect it to approach 0 from below. And so if you plug in infinitely large numbers for x, 1 over x looks like these, and they get smaller and smaller and smaller. So you can say the limit as x goes off to infinity of 1 over x equals 0, because the denominator explodes and the numerator is fixed. So any fixed number over an infinite number is always going to equal 0. Same thing if you go out to minus infinity. 1 over a negative 1 million is just as small as 1 over positive 1 million. It's going to approach 0. If you just keep getting bigger and bigger and bigger numbers in that denominator, 1 over that becomes 0. So it follows that this guy has an asymptote at y equals 0, horizontal asymptote. And so here's the theorem that has if r is positive, so if you got some exponent that's greater than 0, 1 over that to the r as x goes out to infinity is always going to equal 0. So as that denominator explodes in the positive direction, 1 over that becomes 0. And same thing again, if you go out to minus infinity where r is positive, this denominator is going to get huge negative, and 1 over a huge negative number approaches 0. So now they ask us to find the limit as we go out to infinity for this fraction here. If you try and take the infinite limit, you end up with infinity over infinity. It's not at all obvious what this thing approaches. So what you have to do is you first divide both the numerator and the denominator by the highest power of x that occurs in the denominator. So highest power in the denominator is x squared, so we're going to divide each term by x squared. Now when you divide 3x squared by x squared, you just get 3. X over x squared is 1 over x. 2 over x squared is 2 over x squared. And the same thing on the bottom. Now, when you take the limit of this whole thing, you're taking the limit of the top over the limit of the bottom. When you take the limit of these three terms, you're taking the limit of each term separately. Same thing on the bottom. And now we know that the limit of a constant is just that number. And we know that the limit of 1 over x is going to be 0. And 1 over x squared is 0. Anything with a positive exponent greater than 0 is going to go off to 0. And so that one approaches 5. That's 4 times 0, which is 0. And that one is 0. So you simplify it down and you get 3 over 5. Okay, so the limit as x goes out to minus infinity is also 3 over 5 for the same justification. So we know that we have an asymptote at 3/5, y equals 0.6 or y equals 3 over 5. Example 4, find the horizontal asymptotes of this graph. Well, if you divide both the numerator and denominator by the highest power in the denominator, which in this case is x, you divide 3x minus 5 divided by x and you get 3x over x is just 3. And 5 over x is just 5 over x. Now the numerator is a little more confusing because when you divide a square root by x, you have to move that into the square root, and when you do, it becomes x squared. Remember, x equals the same thing as the square root of x squared for positive x, and we're going out to positive infinity, so we can say this. So instead of saying square root of this over x, we can say the square root of the whole thing over x squared. And now when you divide each one by x squared, you get 2x squared over x is 2. 1 over x squared is 1 over x squared. And now you're taking the limit of each one of these four guys. And the limit of a number 2 is just 2. The limit of 1 over x is 0. The limit of 3 is 3. The limit of 1 over x is 0. 5 times 0 is just 0. And so you got the root 2 over 3 is your answer. So y equals square root of 2 over 3 is your horizontal asymptote. Now you want to, if you want to do x as it approaches minus infinity, you have to remember that x is less than 0. And so the square root of x squared is the absolute value of x, or negative x, when x is less than 0. So when you calculate this guy here, you have to replace it with negative square root of x squared because it's going out to minus infinity. And then that negative comes out front and the square root of x squared comes underneath here and divides into each one. 2x squared over x squared is 2. 1 over x squared is 1 over x squared. So now we took this guy here and we divided it by x and we ended up getting that. So you take this guy and replace it with that. On the bottom you divide each one of those by x and you get this. Now you're ready to take the limit, and the limit of 2 is just 2, the limit of 1 over x is 0, 3 is 3, the limit of 5 times this is 5 times 0, so that's 0, and so you just have negative root 2 over 3. And so that is also a horizontal asymptote. Y equals that number. Remember, you find the horizontals by checking infinity or minus infinity. You find the vertical asymptotes where your denominator equals 0, and you can verify that by using the left or right-handed limits. Alright, so if we want to compute this guy, it's not at all obvious what the answer is, but if you multiply it by its conjugate, top and bottom, the top reduces down to just 1, and the bottom is a little more complicated, but again, now if you plug in infinity for x, you get an infinitely large number on the denominator and you get 1 on the top, so that approaches 0. And now you know what your limit is. Arctan, the limit of arctan of this equals arctan of the, you have to figure out what 1 over x minus 2 is for x approaching 2 from the right, slightly greater than 2. So slightly greater than 2 is a very small positive number, and it gets smaller and smaller and smaller. A fixed number over an infinitely small number is positive infinity. So that guy goes to positive infinity. So instead of saying x approaching 2 from the right of this, you can say t approaches infinity of t. Because as x approaches 2 from the right, this guy approaches infinity. So you can just say t and infinity instead of this and 2 from the right. And now we know, if we look at this, arctan of an infinite number is pi over 2. Alright. They talk about the limit of e to the x as x goes off to minus infinity. Well, e to the x is a huge number, but if it's a negative in the exponent, that's 1 over e to that huge number, which is going to be 0. 1 over e to the x. Right, here's e to the x, and as you go off to minus infinity, it approaches 0. So if we look at this guy, and we're coming at it from the left, we're talking about very small negative numbers. 1 over a negative small number is negative infinity. And e to the negative infinity is 1 over e to the positive infinity. E to the positive infinity is huge. 1 over a huge number is 0. So that guy approaches 0. Okay, evaluate sine. If you go off to infinity, it doesn't approach any specific number, so it oscillates between minus 1 and 1, so you have to say it does not exist. Now if you're looking at limit as x approaches, or as x approaches infinity of x cubed, or minus infinity for x cubed, this is going to go off to infinity, this one's going to go off to minus infinity. This one here, again, you've got x squared minus x, and it's not obvious what this is going to approach, but if you factor out an x, you know that this one goes to infinity, and this one goes to infinity minus 1, which is infinity times infinity is infinity, so you know that that goes off to infinity. Now this one, if you divide top and bottom by x, you end up with x plus 1 over 3 over x minus 1. This part goes to 0, that goes to minus 1, that goes to 1, and that goes to infinity. So you've got infinity over negative 1, which is negative infinity. Then if you were to sketch this guy, you would see what's happening here at you can use the limits in order to be able to sketch a graph. As you get closer and closer to larger and larger numbers, you can see which way it goes, and that tells you its left and right hand behavior.